Chapter 6, we look at the numerical approximation of integrals, keeping in mind that integration is anti-differentiation, and since we've used finite difference approximations to approximate derivatives, the question remains, how would we approximate a definite integral? So given a function f of x, we're very interested in being able to numerically approximate an integral of this form. So these will be definite integrals, integrating from a to b, or in this case b to a, either way, doesn't matter. And we'll be looking at the case where perhaps the function is not explicitly known, as in the case of some of the applications we had with the derivative, but we still want to approximate the integral of the function. So this process of numerical integration is also given the term quadrature. And it turns out that quadrature rules are generally more accurate than the typical techniques used for approximating derivatives, especially finite difference approximations. The approach that we use to define quadrature rules is basically a summation like this. I there, the capital letter I, represents our integral approximation, and it's basically formed from the sum of evaluations of the function f, which may or may not be explicitly known, at certain points indicated by x sub I running from 0 to n, so we have n plus 1 of them. Those are called nodal abscissas, as indicated by this term here. And we weight them. In other words, we take a linear combination of those functional evaluations, and those scalars, capital A sub I, are known as weights. So every quadrature rule that we're going to discuss is very simply put in this form. And the key is to come up with techniques to define what the x sub I should be, as well as what those A sub I weights should be. Turns out, quadrature rules can be derived from polynomial interpolations. It's one reason why we talk about the process of interpolation well before we get to discussing numerical integration. So again, these are numerical techniques that you can use to approximate integrals, and is very applicable and comes up in many, many scientific applications. So as indicated on the next slide, you can break down the two groups of quadrature rules into what are called Newton-Cotes rules and Gaussian quadrature. And the basic differences between the two approaches are indicated in this small table. It's very important to make sure you go through each of these and understand the meaning. First of all, in case of Newton-Cotes, those abscissas, those x sub i's, are equally spaced. Whereas in Gaussian quadrature, they're chosen to yield the best accuracy. It's a little bit more complicated with Gaussian quadrature, but you'll see later when we cover that, the derivation of those rules, they're not going to necessarily be equally spaced. The assumption with Newton-Cotes is that you can evaluate or obtain those functional values at equal intervals, whereas in Gaussian quadrature, we're trying to minimize the number of nodes in the sense that perhaps the function might be expensive to compute. Whereas in Newton-Cotes, the function is assumed that it's cheap to compute, it's computationally not taxing to get new functional evaluations. And again, we're going to start off looking at how we can use local polynomial interpolation to derive these Newton-Cotes rules, whereas Gaussian quadratures are very effective at handling singularities. Singularities in the sense of integrating a function like this from between 0 and 1 when we know that that denominator term cannot be 0, and as x gets closer to 1, we have a problem with that integrand. So that's the basic differences between Newton-Cotes and Gaussian quadrature. We'll discuss how both work, how they're derived, and how they can be used for numerical integration. But it's very important to see right at the offset how they're different. And we're going to start off with Newton-Cotes rules, which are derived from simple polynomial interpolation. So let's start off with Newton-Cotes formulas. The idea is that we have our function indicated in this green curve. Again, at the x-axis is the horizontal axis, and we'll say f of x, or the y-axis if you want to call it that. Y equals f of x is on the y-axis. And the green curve you see there represents the function. And what we're going to do at our abscisses, our grid points, x0, which we'll say is equivalent to a, xn is equivalent to b, and then we just indicated numerically all the other abscisses. So that's a grid that we lay out on the x-axis. And what we'll do is we will build a Lagrange interpolant on each of those subintervals, but we're going to build a Lagrange interpolant over those abscissa points, and we'll call it P sub n of x for those n plus 1 data points. So it will be unique. Again, it'll be of degree n, but it'll be interpolating to those n plus 1 points. All right. And again, we're constructing a polynomial approximation of f, and we're going to use this polynomial to help us produce representations of the integral of the function. Keep in mind from your original definition of integration, when you had your in your Calculus 141 courses, the area under the curve there represents the integral. And so we're going to be approximating that area, and we'll do it along these in these subintervals as we move from A to B. So if we go back and remember our construction of Lagrange interpolant, what we're trying to do is we will interpolate to those data points using our function Pn of x. So what we'll do is after we've constructed that polynomial, we'll integrate it. The assumption is that it's a lot easier to integrate a polynomial than some perhaps complicated function involving trig functions, or square roots, or just more complicated functions. So we'll use polynomial to interpolate to the data, and hopefully the area underneath the polynomial will be very good fit to the area under the curve for the original function f. Going back to our definition in terms of the formulation of the Lagrange interpolant, remember our cardinal functions Li of x, weighted by the function evaluations f of x, I. So again, what I've done is I've just replaced our definition of how to construct a Lagrange interpolant inside this bracket here, which represents P of x. And then basically, if we just realize the fact that we can pull the f of xi's out because we're integrating with respect to the independent variable x, and those x of i's are specific scalar values, what we've got is a quadrature rule of the form we were talking about before, where in this case we have the f of xi values that we wanted before, but our weights are given by the integrals of our cardinal functions. But the hope here, of course, is those Li of x's are very simple to integrate. And if you go back to the derivation we did of the polynomial interpolants, yeah, they were very simple. They were either linear, cubics, quadratics, depending upon the degree of the polynomial, the overall polynomial we were using to do the interpolation. So we're going to look at these cases. If n is equal to 1, which means you have 2 data points, that's called the trapezoidal rule. If n is equal to 2 and you have 3, that's called Simpson's rule. And then if you actually had 4 data points, that's a variation of Simpson's rule called Simpson's 3/8 rule. So we're going to start off by looking at, well, what if you use 2 data points simply to construct basically a linear interpolate to your data and use it as a way of getting an integral estimate of the original function. Well, as indicated on the next slide, there it is. If you only have 2 points as you go from A to B, so if we're integrating from A to B, the green curve is the function, and we're only going to build an interpolant to those 2 points. So x0 is A, x1 is B, then clearly what you see is you have a straight line. That's the interpolant, right? Okay. And so if we were trying to use the area under that polynomial, which turns out to be a straight line or a linear function, we are going to have some error all this shaded area up here in yellow there, which is definitely underneath the function, the original function f, which is here, there's going to be some errors. So clearly, sometimes this might be good. If there's a large variation here with a function, this is not necessarily good, but I've exacerbated the error. Many times, it's actually a pretty good fit, depending upon the distance x0 is from x1. And that might be one way to reduce some of this error, is to choose many more points and still do linear interpolance on each one of those, and we'll talk about that in a second. But for now, here is the Lagrange interpolant constructed for the points x0, f of x0, x1, f of x1, right? And those are the cardinal functions that we would canonically generate, just substituting the fact that x0 is a and x1 is b. These are the two representations of the cardinal function. So then the first weight is integrating the first cardinal function, and we can see in that case, if we just substitute what L0 of x is over here and do the integration, we can get that the weight is h over 2. Right? So what we know is that we need to take h is the distance here between a and b. We need to take half that distance as the weight on our first function evaluation. And if we go to the next slide, you can simply do the same approach to integrate L1 of x from a to b. There's the algebraic expression for L1 of x. It's got to be linear for this linear interpolant. Both L0 and x and L1 of x have to be linear for a linear interpolant of Lagrange form. Well, it turns out the weight is the same too. We actually integrate that and come up with h over 2. Very, very simple integration, just doing very simple integrals of x dx, is x squared over 2 and so forth. So the quadrature rule we've come up with is this, that the weights are h over 2, and you can write f0 of x and f1 of x, but we typically like to write it in terms of the terms used in the original integral, which was from a to b. So that is a quadrature rule. That's a way of estimating the integral of f from a to b, keeping in mind that we definitely have some error. Now this shouldn't be surprised, because if you look geometrically here, what is this area that we've just used to approximate the area under the curve? Well, that's a trapezoid, right? And if you think about, well, what's the representation of a trapezoid, right? Well, it's 1/2 the base times the sum of the two sides. Well, this is the length f of a, that's the length f of b, and this is the base h, and you take half of it. So if anything, it's easy to remember these rules if you just think geometrically, what kind of area are you using to approximate the area under the curve, which is the integral. Okay. Now, pictorially, we can see what the error is, but algebraically, you can actually pretty much come up with a representation for the error for using the trapezoidal rule. And it turns out you can come up with an expression that looks something like this. Again, if you're integrating from a to b, the error is going to definitely depend on how wide or the size of that subinterval. So the distance b minus a comes into effect, as well as the second derivative of the function somewhere on the interior. Okay. So overall, the error could be represented if b minus a is the distance h, it's order h cubed over 12 times a certain internal value of the second derivative. But for the most part, that error is going to be controlled by h, assuming that you don't get something really crazy in the second derivative. So another way of representing what the error is again looking at that the exponent on the h. And in terms of big O notation, we would say that the trapezoidal rule would be order h cubed in terms of accuracy. Okay, so you can control that error by looking at estimating what the cube value of your distance h is going to be. If it's 1/10 or 1/100th or 1/1000th, whatever, you now have sort of an estimate of how much error you're probably going to accumulate if you use this particular rule on your on the interval of interest. So you can take this process and break your problem into many subintervals. And if you did that, that has a name. It's called the Composite Trapezoidal Rule. In other words, instead of just going from A to B with one linear interpolant, for example, we will use several linear interpolants. We'll break the problem up into a mesh from x0 to xn. x0 is A, xn is B, and we'll have several subintervals. But keep this in mind that the distance between all your abscisses is the same. It will always be h. Remember in that table, this is a Newton-Cotes rule, all the abscisses are equally spaced. So what we have is the area for this first trapezoid, and then we add to it the area for the second one, and so forth. And we need to compute all n of those areas. They're indexed from 0 to n minus 1, so therefore we have n of them. So we have n trapezoids. The algebraic formula is just a representation of summing up all of those areas, and that's what it is, because again, the base is always going to be h for each one of those trapezoids, so the area is going to be h over 2, and then notice that you'll have the first f of x0, the first functional evaluation, plus 2 times f of x1. All these interiors will be using the functional values twice, except at the beginning and the very end. You only have one trapezoid that involves f of x0, and you only have one trapezoid that involves f of xn. So this is called the Composite Trapezoidal Rule, and it does fairly well. The overall error for doing this entire process on your interval is of the order minus quantity b minus a times h squared. Again, if you keep in mind here now that h here is not the same as b minus a, right? H is very, very much smaller. It could be b minus a divided by n, depending upon your choice. But this is going to be pretty much h cubed like in terms of the error. But notice that the error, again, we know this, that the error on any one of those panels, one of these specific trapezoids, will be of that form, which is what we said in the previous slide. So in each subinterval, our error is about order of h cubed. So thinking about summing that across, or accumulating that across all the trapezoids, it'll still be basically order of h cubed. But a very nice technique. And you can even see from the picture that sometimes, depending upon how the function wiggles here, and I've done this just to show that there are errors, but sometimes, maybe the function acts very linear and the error will be very low. If we look at an example of using these Newton-Cotes rules for approximating intervals, problem 2 is a very nice little problem in problem set 6.1 on page 212. This is a very canonical physics problem. I just want to illustrate how you can use, say, the Composite Trapezoidal Rule to approximate an integral that will come up in this type of application. So suppose you have the power P supplied to the driving wheels of a car as a function of its speed v. So power is assumed to be a function of v, which is the velocity, and the mass of a car is 2,000 kilograms. The goal is to determine the time differential it takes for the car to accelerate from 1 meter per second to 6 meters per second. And this is an application of Newton's law. So Newton's law says force equals mass times acceleration. You should remember that from physics class. But acceleration is just nothing but the derivative of velocity. So again, we assume that power is a function of velocity given in this formula here. In fact, power is equal to the force times the velocity. So exploiting Newton's laws then, what we really can write is that we can say, well, then power is really equal to the mass times the derivative of velocity with respect to time. Okay, all right. So now if we know that power is a function of velocity. If we, and let's not forget that this must be multiplied times v, all right, because the force is equal to this term right there, and that has to be times v. But we realize that what we would like to do is try to see if we can, determine one of these, if we can determine what v is, then we should be able to determine what the power is at any time and exploit the fact that, well, it's a derivative with respect to time. So what we need to do is see if we can isolate some terms and get time on one side. So you can do that, multiply both sides by dt, and then divide both sides by p, and what you could easily get is that this dt would have to be m times, let's see, v over p times dv, okay? And then just realizing if those quantities are equal, then their integrals are equivalent. And so what we're doing, and then integrating dt is just t, but we'll represent it as delta t up there. But what we really have is that to get the time that we need to go from 1 second to 6 seconds, and so this is the definite integral 1 to 6 of this term, which is indicated up there, mass times v over p times dv. Okay, so doesn't look exactly like the canonical problem integral ab f of x dx, but it's similar because the function is just this ratio v over p. P is assumed to be some function of v, and then the dx is going to be dv. All right, so we're going to use the composite trapezoid rule to approximate this, and then this integral, and then we have to remember that, oh, okay, whatever we get, we've got to be able to multiply it times the mass, and that'll give us the final answer here that we want, which is delta t. So I'm just using delta t to represent that t there, okay? So we would have to have data. We'd have to have the velocity, we'd have to have the power, and then we have to have the ratio at each one of our grid points, okay? That's, again, what we have to do. And that has to be multiplied by the difference in velocity as we move through there, okay? So if we go to the next slide, here the data is there, and the representation of the composite trapezoid rule is there. So let's look at the rule first. So the integral that we're trying to approximate is this one. So this is a representation, taking the formula for the composite trapezoid rule, and realizing that the function will be evaluated at I and I plus 1 points, and here's our representation of it. It's just that ratio v over p. And then we need to multiply, each of the trapezoids will have a certain length, and there'll be the difference in the velocities. So everything is a function of velocity in this case. So let's look at the data points. We're going to be integrating from time 1 to 6, but we actually have 7 data points. We need the initial velocity, the initial power, and then of course, then if we have those, we initially know what v over p is at the initial point. So what we're doing is we're laying a grid out here from, say, v0 to v1, v2. So there are increments of our adjustments in velocity, okay? V4, I'll go ahead and draw them in just so we can understand how this grid is being used. And so on each one of these grids, we're generating, it's kind of cool, I can do that. We're generating a trapezoid, okay? So we're trying to get a trapezoid here, and then another trapezoid there, and so forth and so on. So, oops, the selection thing drives me crazy. And then you get the idea as you go through the trapezoids. And so we have to represent the area for each one of these trapezoids. That's T1, T0, this is T1, and this last one, I'll just sort of sketch out here, will look like well, let's see, that would be T5, okay. So there will be 6 of them, all right? So there's 6 trapezoids. And so each time what we have to know is the difference in velocity. Well, that's easy to get. You can see the first one's going to be 0.8. The next one's going to be 0.6. I'm just subtracting the differences here. And the next one would be 1.1 and so forth, okay? And what we need to do then is use these ratios of, you know, for this example, if we go to the very first one, we'll need to know what we need to know the sum of the bases there, and the basis will be given by these ratios here, okay? So in the first case, we'll have 0.2128 on this height, excuse me, not the base, and this height would be at V1 will be given by that value, okay? And those will be added together, okay? And so you'll go through and determine each one of those areas, and you would add them up. And then when you sum up the area of all those trapezoids, you would get this value, 1.2984. Okay. Again, you're just using this rule to add the two heights and multiply times the difference in velocities. That's just the length of each of your bases for each one of your trapezoids. Okay. Easily done, easily computed. Not so well by humans, but easily a very simple program. And you would get this value. And then we would go back, remember, because the problem said the time differential is the mass times that. So, and of course we have to multiply by 1/2 when we add all those areas up. So let's do that first. So the integral we just determined would be 1.2984 divided by 2, which of course is equal to 0.6492. That would actually be in meters per kilonewtons times seconds, if we want to be exact on our K and S, right? And then the answer in terms of how much time it would take, you would multiply that value times the mass. And it turns out with all the units perfectly canceling out because the mass was given in kilograms. Can't seem to, trying to get this to be an equal sign there. There we go. So this is going to be actually 1 point. All the units kind of cancel out there because of that 2 factor and some unit changes. You will turn out the answer will be 1.2984 seconds. Okay. Right. So very interesting. So it takes a little bit more than a second, but not quite 2 seconds to, if we go back to answer the question, how long does it take for the car to accelerate from a velocity of 1 meter per second to 6 meters per second? Just under 2, certainly somewhere between 1.3 around that seconds to get that kind of acceleration, which is basically pretty fast. So that's just a very simple illustration of using the composite rule. And again, keep in mind, we don't know explicitly what this function was that describes this problem. We're just given data points and representing the fact that we know this linear relationship between power and velocity. Right? So we'll continue on in our next lecture by looking at a more efficient way to generate the trapezoidal rule, and then go on and look at some other polynomials that can help us build quadrature rules.